Hi, my name is Maria Telleria. I am a graduate student at MIT and I study mechanical engineering. In this video, I'm going to tell you all about beams, how we use them, and how do we design them to get them to achieve the desired performance. Let's start with a quick definition. A beam, such as this one, is a structural member that is able to withstand loads. In general, they have one dimension that is larger than the other two. The beam has to be able to support its own weight as well as any external loads placed on it. It might seem like it's very easy to design beams, but if they're not designed properly, they can fail catastrophically. Take, for example, the Tacoma Narrows Bridge. In this video, what we're going to see is that when the gust of wind hit the bridge, it actually caused it to deflect and eventually to fail. So how do we make sure that our beams don't fail like that? First, we need to talk about stress. Stress, denoted sigma, is defined as the force per unit area. This tells us that both the force that you're applying as well the area that you're applying it over with are important. A good demonstration of this is just take a pencil. If I press down on my hand with the eraser side, I can press down pretty hard and not feel any pain. Whereas if I use the pointed end, pretty quickly I feel some pain. That is because the area in the pointed end is much smaller, which gives us a much larger stress on my hand. An important thing to understand about stress is there's a maximum stress that things can take before they fail. We're going to use a plastic beam to demonstrate this. I'm going to use safety glasses just in case. We have a plastic beam here. As I load it, we can see that the beam deforms. The stress has been low enough that the beam has not failed. However, if I keep loading it, there's going to come a point where the beam fails. The stress was too high that the beam fractured. There's another way that beams can fail. The other way is through plastic deformation. If we take, for example, this aluminum beam here, if I put a small enough load, it returns to its original position. However, if I put a larger load, we see that I have deformed the beam and it cannot return to its original position. The beam has plastically deformed. We need to make sure that the stress that our beam has is lower, actually let's say much lower, than either one of these to ensure that our beam will not fail. Strain is denoted by a small e, and it's defined as the change of length per original length of the material. It doesn't only matter how much length you're changing in the beam, but also the original length of the beam. Think, for example, if you have two classmates. You had a pretty short classmate and a pretty tall classmate. Over the summer, they both grew an inch. We'll represent this by growing the size of a head. Okay, so this guy also grows the same amount. Even though they both grew the same amount, delta L, let's call it 1 inch. So delta L here is 1 inch, and delta L here is 1 inch. The original length of this guy was, let's say, 10 inches, whereas the original length of this guy was 20 inches. The strain then will be 1/10, and the strain for this guy will be 1/20. As we see, the shorter classmate exhibit larger strain over the summer vacation. Before we move any farther, I want to make sure that we understand the units of these two. The strain is actually unitless, because if we think about the units, the change of length will be measured in meters, and the original length would also be measured in meters. So it is a unitless measure. Whereas the stress, force is measured in newtons, and area is measured in meters squared. That gives us newtons per meter square, which we call pascals. So we'll put pascals here. Both stress and strain are very important when we're talking about beams. There's actually a material property that relates the stress on a material to the amount of strain that it will exhibit. This material property is called the Young's modulus of the material. It's denoted capital E, and it is a measure of the stress needed to achieve a given strain. Again, if we look at the units, this was pascals and this was unitless, so this will again be a pascals. The best way to understand the Young's modulus is to look at a graph of the stress versus strain. So we're going to have a graph here where we're going to have stress on the y-axis and strain on the x-axis. The way these graphs are collected are actually in machines that test samples. The samples usually look something like this, where there's a necking section. And what the machine does, it pulls on the sample It measures the stress that it needs to pull on the sample with, and then records how much the sample deforms under the load. What we end up getting is something that looks kind of like this. There's a straight portion, then there's a bend, and usually there's a limit. The straight portion here, if we look at it, is a slope, which is the stress versus strain, which we already said is the Young's modulus of the material. So that's how we get the Young's modulus of material. When we see this bend, this is actually the yield stress of the material. It's the point at which the material stops behaving elastically and starts behaving plastically. This endpoint is usually the fracture strength or the maximum strength of the material. So we denote it fracture. This is a typical graph for a common material such as steel or aluminum. Most metals behave in this way. The area moment of inertia, denoted I, about the x-axis is defined as the areal integral of y squared dA. If we work out this integral, what we find for this rectangular beam is that it is bh cubed over 12, where b is the width of the beam and h is the height of the beam. One thing to note right away is this cubed right here. This tells us that the thickness of the beam is much more important than the width of the beam. So if I want to change the area moment of inertia of our beam, the easiest way to do it is to increase or decrease the thickness of the beam. So this is our equation for the deflection of the tip of the free end of the beam. And again, the first thing you should notice is this cube term again here, which tells us that the length of the beam is going to be very important in calculating its deflection. If we were to expand the area moment of inertia, which said bh cubed over 12, again, the thickness of the beam is very important. The other thing that we're concerned about when we're designing our beam is to ensure that we're not exceeding the yield stress of the beam. So we need to calculate what is the stress on the beam under this load. In reality, both the weight of the beam and the load are putting a stress of the beam. But for now, let's focus on just the external load. To calculate the stress on the beam, we need to understand the bending moment on the beam. So think about back to your physics classes where you were talking about like levers and fulcrums and things like that. So if we had a lever where we were using it to lift this box here, when we calculated the moment on it, we used not only the force, but the length of it to figure out what the moment on the rock was. So moment is defined as force times the length from which it is applied. Same thing occurs here. So the moment is going to be the force times the length of our beam. Then the stress equation for the beam is going to be the moment on the beam, which is F times L, times y over, again, the area moment of inertia. Y signifies the distance from the neutral axis. So again, let's look at the cross-sectional area of our beam. This is this area right here, where we have a neutral axis at the middle, which is going to be the x-axis, and this is the y-axis. Right away, what you should see is that the stress is going to depend along where you're looking in the beam. If you're looking right at the neutral axis, y is 0, so there's no stress. If you're looking at the very edge of the beam, that's going to be the highest stress because that's as far away as we are from the neutral axis of the beam. The displacement, as we talked about before, is FL cubed over 3EI, and that gives us about 35.4 millimeters under this load of displacement of the tip of the beam. And then we're going to calculate the max stress. The maximum stress, as we discussed before, is going to be at the edges of the beam, and that occurs about half the thickness away from the neutral axis. So we use F times L, which is our bending moment on the beam, half the thickness of the beam, and our area moment of inertia. And we calculate that to be about 47 megapascals. This is well under our yield stress of 300 megapascals, which means that once we remove the load, the beam should return to its original position and it will not have plastically deformed. So here we have our beam. It is clamped on one end, free on the other end, it is not touching the wall, and we have a ruler stuck to the wall to measure the deflection. I will go ahead and load it with 50 grams so we can see the deflection. We see that the beam displaces approximately the 35 millimeters that we predicted. When I remove the weight, the beam returns to its original position because we did not exceed its yield stress. Hopefully you can see that beams are critical in our everyday lives. They're in the buildings around us, they're in diving boards, they're everywhere really when you think about it. And hopefully you've also discovered that it's very important that we design these properly so they don't fail. I encourage you to learn more about these because there's many things we haven't even touched upon. For example, stress concentrations, creep, and resonant frequencies of these beams that we also have to worry about when we put them in buildings. So how do we make sure that our beams don't fail like that? First, we need to talk about stress. Stress, denoted sigma, is the... Hi, my name is Maria Telleria. I am a graduate student at MIT and I study mechanical engineering. In this video, I'm going to tell you all about beams, how we use them, and how do we design them to get them to achieve the desired performance. Let's start with a quick definition. A beam, such as this one, is a structural member that is able to withstand loads. In general, they have one dimension that is larger than the other two. The beam has to be able to support its own weight as well as any external loads placed on it. It might seem like it's very easy to design beams, but if they're not designed properly, they can fail catastrophically. Take, for example, the Tacoma Narrows Bridge. In this video, what we're going to see is that when the gust of wind hit the bridge, it actually caused it to deflect and eventually to fail.